The thermodynamic property relation. At this point, we derive two important thermodynamic relations for a simple compressible substance. Compressible substance, we have these relations TdS du plus Pdv and TdS dH minus Vdp. The first of these relations can be derived by considering a simple compressible substance in the absence of motion or gravitational. In the absence of motion and gravitational forces or effects, the first law of for a change of state under this condition first law for a change of a state, we can write delta Q du plus delta W. The equations we are deriving here deal first with the change of state in which the state of the substance can be identified at all times. Thus, we must consider a quasi-equilibrium process. For a quasi-equilibrium process, to use the term introduced in the previous chapter, a reversible process. A reversible process. For a reversible process of a simple compressible substance, we can write and also delta Pdv. Substituting to the previous equation, we can obtain to this equation Q delta Q in exact differential of Q because it's a path function, TdS du plus Pdv. This is the first equation when we set how to derive. Note that this equation was derived by assuming a reversible process. This equation can therefore be integrated for any reversible process or during such a process that the state of the substance can be identified at any point during the process. We also note that this equation deals only with properties. Suppose we have an irreversible process taking place between the given initial and final state. So deal with only properties. Now suppose that we have a irreversible process with given initial and final state. And final state. The properties of a substance depends only on the state, and therefore the change in the properties during a given change of state are the same as for an irreversible process as for a reversible process. The state the properties of substance is only dependent on the state. So the relation TdS du plus P dV can be applied for irreversible process also. Irreversible processes. Therefore, this equation is often applied to an irreversible process between two given states, but the integration of the equation performed along a reversible path between the same two states. But the integration of this equation is performed along a reversible reversible path between the same two states. Since enthalpy also HU plus PV is follow as DH DU plus PdV plus VdP. So this expression DH minus V dP equals to du plus P dV, which is equals to T ds. A relation for the enthalpy, which is the second relation that we set out to derive. These two expressions is equation T ds du plus P dV, and then next is T ds Th minus V dP. Two forms of the thermodynamic property relation and are frequently called Gibbs equations. Thermodynamic property relation. Gibbs equation. This equation can also be written for a unit mass. TdS du plus Pdv and Tds Th minus Vdp. The Gibbs equation will be used extensively in certain subsequent sections of this book. Gibbs equations. If we consider substance of fixed composition other than a simple compressible substance, we can write TdS equation other than those just given for simple compressible substances. We noted that for a reversible process, we can write the following expression for work. For a general process, we have delta W P dV minus dl V dA, and the electricity 4 plus, for a general case, we have du plus P dV minus the tension, the surface tension, and also the electricity work. Entropy change of a solid or liquid also in this next section.